Using this large scale conference and handling is very nicely, and I am going to talk about how does long range order affect Cooper pair formation in quasi-periodic systems. So I have talked about this walk I think a few months ago in somewhere else. I can see some very few common faces in the audience, but I can assure that I will be discussing some new results also. And of course the acknowledgement, all the support that we get continuously by the Department of Space at PRL, and of course the cluster that without which it was impossible. Okay, so how does long range order affect Cooper pair formation in quasi-periodic systems? So of course I will be defining the quasi-periodic systems which has basically the long range order, and then I will be showing the results for the Cooper pair formation. And then I will answer the question that how does the long range order affect this Cooper pair formation. So first of all, we are not confirming any superconductivity in this work. I will be just talking about the formation of Cooper pair. So you can see that in a quasi-periodic systems, I am showing the results for order parameter. So you can see this the parameter space is the one direction is the chemical potential, and something that we define is the co-number. And we can see this is basically not uniform, it has a certain distribution, and I will describe, and of course I will come to that result at the end of my talk. I will come back to this figure plot. Yeah. So quasi-periodic system consists of structural patterns which are ordered but not periodic. So it has a certain periodicity, but it is not the complete periodic. So if I look at a very few lengths, very few I think the bond, if I discuss define the lattice constant by A, and if I look at a few A, and that I will not get any kind of pattern there. So I have to look at a very long scale to get some certain pattern. It shows the complex Bragg diffraction patterns. The energy spectrum is highly fragmented, is Cantor-Sen spectrum, and the wave functions are mostly neither localized nor extended. That is the interesting fact that that's why people are actually interested in this kind of systems. I am showing here the density of state for a simple 1D wire. You can see this basically the continuous density of states, but it gets fragmented once I include the hopping ratio is different from 1. And as soon as I increase the hopping ratio, either it's away from 1, either it is smaller than 1 or larger than 1, and this opening of gaps basically increases with the hopping ratio. And the examples, a few examples have been mentioned, I have mentioned here, like Fibonacci, silver mean, copper mean, Thumos, etc. Concept of quasi-periodic sequences has been extended from abstract mathematics to various branches of physics, and people have studied this kind of quasi-periodic systems from different perspectives. Different substitution basically impose distinct spatial correlations, and the sequence dependent transport properties, fractal properties, and the multifractal analysis, people have already done it. And interestingly, quasi-periodic systems can also host some non-trivial topological phases, but I should admit here today this is a section for unconventional superconductivity, but I will not be talking about any unconventional superconductivity, but I have not found any suitable section for this, so this is the most closest one that I have figured out. So why I am interested in this kind of systems? So recently it has been shown that in this kind of a quasi-periodic systems, we can have a superconducting ground state, and then they have used basically aluminum, zinc and magnesium quasi-crystals. And not only, but the TC is extremely low here. So the question can appear that what type of materials or how to get the higher TC, so that it is little bit better than the situation here. Not only this one, and there are also some works, I have mentioned here some of them. So like enhanced TC in 1D incommensurate systems with S-wave pairs, superconductivity and a quasi-periodic lattice. Then they have basically discussed the extended to localized crossover of Cooper pairs. And there are some other works including Fibonacci chain, and then also order parameter fluctuation, Josephson effect, and the charge density wave. So the question that we are asking, how quasi-periodicity manifests superconductivity, but sorry, I should actually correct this question here a little bit. It is not the superconductivity, it is the Cooper pair formation only. So to understand the effect of quasi-periodic sequences on the Cooper pair formation, what we do, we take a toy model. Basically it's a 1D where all the atomic sites has a particularly same on-site potential, and we set it to 0. And the hoppings that we take is following a particular quasi-periodic sequences. You can see that we have basically two different types of hopping, TA and TB, and that are organized in a way TA, TB, TA, TA, TB, TA, and this is the Fibonacci sequence that I am showing here. So Fibonacci sequence is very well known. It follows the growth rule. Something like A, I have to replace, suppose I have a two number A and B, and A have to, two letters, and then A I have to replace by AIBJ, and B I have to replace by A. Now the question is, what is the value of I and J? Depending on the value of I and J, we can have different type of sequences here. For Fibonacci sequence, I equals to 1 and J equals to 1. So basically I will be replacing A by AB and B by A. So if I start from A, I will have something like this, A, then I will be replacing by A by AB, and then again A by AB and B by A. So the next series will be ABA, and the next generation will be AB, AAP, and so on. So total number of bonds that we can also find out from there is Fn plus 1. There is a particular n plus 1 generation equals to, and that can be defined by this rule. And if I start from F0 and F1 equals to 1. And in the large n limit, basically the ratio of Fn plus 1 by Fn, that follows this golden ratio. If I choose I equals to 2, keeping J equals to 1, and I will get the silver mean sequence, and then that means I have to replace A by AAB and B by A. So it follows this generation something like this, A I have to replace by AAB, and then again AAB, I will be replacing B by A, and B by A, and this A again AAB. So it seems like AAB, AAB, A, and again in the long, for in large, this Fn by Fn minus 1, that will give you the silver ratio. Exactly in a similar way, if I keep I equals to 3, keeping J equals to 1, that means I am replacing A by AAB and B by A, and then I will get a bronze mean sequence, and which is defined by basically the bronze ratio. So I define all these three different types of the quasi-periodic sequences as a periodic binary system 1. Why? The similarity is that I am only changing I here in here, keeping J equals to 1 always. Then one can also change J keeping I constant, and that means I can generate the other two sequences. I am taking some examples here. So copper mean chain and the nickel mean chain, where I will have A, suppose I equals to 1 and J equals to 2, that means I am replacing A by ABB and B by A. For nickel mean sequences, I think it is A, I have to replace by A, B, B, B and B by A. So basically in the previous one, and this I had defined by ABS2. So in ABS1, if I look at the three different sequences I am considering here, so I am basically generation to generation I am increasing the number of A's more compared to B. Exactly in the other case for ABS2, I am increasing the number of B more than A. Okay, so for the simplicity, let us take a toy model. I am going back to the toy model that I have shown previously, but there can be a question of one day the superconductivity context, and at the same time we are considering basically an attractive Hubbard model. So of course the one day will be question here. So I will show you in the upcoming slides that's all the results that we have found here, and whatever the explanations that we have found here, all these are valid qualitatively in the 2D cases that we have already shown here. I will show it next. So as I mentioned that we are considering an attractive Hubbard model. So this Tij is and we are considering basically the bond model. That means the Tij, it can take the value like Ta or Tb as I shown previously, and then these on-site potentials we have kept at 0, and the mu we have considered different kind of fillings that I will come back, and this is the Hubbard strength, and we are considering only the on-site pairing. So what we do that we solve the order parameter self consistently, and let us see what we are getting here. So first let us start with the Fibonacci chain. Fibonacci chain, the order parameter basically it's split into two different branches. This blue color corresponds to the Fibonacci chain. So order parameter for the periodic chain, one can find just replacing this TA or TB. So I can set them as equal to each other. Considering two different values. So for Fibonacci chain, what I am taking here for TA equals to 0.25 and TB equals to 1, where I generate the corresponding periodic counterpart by considering either TA and TB both 0.5 or 0.25 and or TA TB both are as 1. So what we get basically, the periodic chain gives me the two different limits. One is set by this black line and the another one is the red lines. Once I go to the Fibonacci chain, that means I set the TA not equals to TB, basically TA less than TB. I see that basically the order parameter basically it gets split. So how to read this? Each dot basically represents the order parameter at each side index. So basically these are oscillating but dividing majorly in two different branches. If I go to the other parameter space, so TA basically exactly the opposite. I say TA equals to 1 and TB equals to 0.25. I say that okay, again we have the two different branches for the Fibonacci chain, and these are the corresponding periodic counterparts, but the value is much reduced compared to the previous parameter regime. Now if I move to the silver chain, see that for the first parameter regime, basically again we can think about a very local fluctuations here. Roughly we have again two branching thing, and again if I just change the parameter regime and go to the reverse parameter regime, it shows the two branching phenomenon but with the reduced order parameter value. Coming to the bronze mean chain, again getting the similar result, but here the parameter value is much more reduced compared to the other cases because of the low number of sites, and at the same time there are some other factors that I will describe later. So the question is why? How to understand that? How to describe this behavior? To describe this behavior, we are considering two different space. One is the co-number space, another one is the real space. In the co-number space, but for both the descriptions we need to identify basically the different environments. How to define that? If I look at the 1D chain, I have either TA, the next nearest neighbor hoppings, or TA-TB or TB-TA. So I define this TA-TB or the sites flanked by TA-TA, that we will call alpha, and in between TB and TB we call it beta, and the other two TA-TB or TB-TA that we call as gamma. So that means we have three different kinds of environments here. So I have shown the two branching phenomena in this kind of Fibonacci in the behavior of order parameter. It seems like I have taken now two different type of hottings and that is giving me two different branching, which is actually not true. So I will explain in the upcoming all the slides. So for the Fibonacci, if I look at this particular TB is absent. Basically beta type of sites, I don't have beta type of sites. I will have either alpha or gamma. So now we define the co-number for ith side. How to define this co-number? Co-number will basically give me the is a particular for ith side, the Ci is defined in this term. So where Gn basically is the generation of particular sequence, whatever sequence that we are considering. So to understand the co-number representation a little bit more, I show here the co-number space description for the spectral properties. So if I look at this generation 2, the mod chi-square behavior, this is the density plot in the energy index and the co-number index. We see that the highest amount of mod chi-square value that we can get around this region. This is if I go along this horizontal axis, this co-number index from this one and to this one, this middle one basically gives me the alpha type of sites, but the other two basically correspond to the gamma sites. So what we are getting that, and this is the roughly around the half filling. So what we are getting basically for the half filling, the co-number space, the order parameter contribution mostly coming from the alpha type of sites. This is the mod chi-square value. And next way, if I move to G3, there is a next generation, again the same similar things following, and there is a little bit change in the magnitude. Next let us move on to G4. Now G4, we see that basically the central region is almost similar, but this picture is coming here again, is coming back, and that is the self similarity property of a quasi periodic system, that's showing here. So as I mentioned, this alpha and gamma size, we have this in the Fibonacci sequence, we have only alpha and gamma size. This corresponds to this region, this strip corresponds to the alpha size, and the other strips correspond to the gamma size. And then if I move on to the higher generation G5, G6 and G7, you see the similar similarity property is coming back continuously. So now let us coming back to the results of order parameter. Now we plot delta I as a function of co-number index, and in the middle region, as I mentioned previously, we have only these alpha sites. So we had the two different branching in the order parameter behavior when we looked at as a function of a site index, but here we can basically we can group the based on the contributions coming from the alpha or gamma sites. So all these alpha sites are contributed much majorly to the order parameter behavior, and this is for this particular parameter regime. If I move on to the next the reverse parameter regime, what we see that now these alpha sites, they are not showing the higher value, they are lower, but I can't say at the same time that is not, the behavior is not exactly opposite. That means all the gamma sites are not showing the higher one. A few gamma sites which are showing higher order parameter, but a few gamma sites are not. So how to understand this? And if I plot the Morshai square here in this for the same generation, we see that there is a tendency of clustering around these alpha sites. Basically those alpha sites are giving me the higher order parameter, and if I move to the other parameter regime, it's actually spreading out towards the gamma sites mostly. Now we cannot identify which gamma sites is giving me the higher contribution, and to identify that, let us move on to the real space picture. And the real space picture, I will be again using the similar definition that I have mentioned previously, those alpha, beta and gamma sites. Let us see how it behaves. So for the sake of understanding, I am showing here very small generation Fibonacci chain. So as I mentioned previously, there are two branches in for this particular parameter regime, and if I now show the order parameter value at each sites, it gives me these two different types of distribution. So we see that at all these alpha sites, the order parameter is much higher, but for the gamma sites is much lower, and exactly the similar thing we had previously. Now if I move on to the reverse parameter regime, now there is interestingly, it is not exactly the opposite. Now all alpha sites are basically giving me the lower order parameter, but not all gamma sites are giving me the higher order parameters. There are some gamma sites which are basically giving the lower order parameter as well. So how to identify these gamma sites? So we have identified in a way that all the alpha sites are sitting in between gamma, alpha, gamma in these environments, higher those gamma sites will be showing the higher order parameter. Now this was for a smaller chain. Now if I move on to come back to the same size for which I have shown the results previously. This is exactly the same plots which I have shown in the previous slide. This is not a new result. So but we see that for the ABS1, this is I am showing only the result for Fibonacci here. So all alpha sites will give me the higher order parameter, whereas the gamma sites will give me the lower order parameter. For the other parameter regime, gamma sites within the gamma, alpha, gamma and will only give the higher order parameter. The rest will be showing the lower order parameter. Now coming back to the silver mean chain, silver mean for this parameter regime, the behavior is very similar to the Fibonacci chain. But if I move on to the reverse parameter regime, now I have to basically identify similarly this gamma, alpha, gamma sites. So it tells me that it is not the nearest neighbors, I have to go to the next nearest neighbor regime. I have to consider the next nearest neighbor as well. So for the bronze mean, I have to basically now have to move on, and then I have to identify it does not depend only on the gamma, alpha, gamma. I mean not only the next or nearest neighbor or next nearest neighbor, I have to consider further environments to identify that which sites is giving me what type of order parameter. So this was the summary of the growth rules that I have already shown previously. So if I go to the ABS2, Because of the shortage of time, I will basically summarize. For the ABS2 type, where I was basically increasing the number of TBs continuously compared to A. So, I see that I told actually a few minutes ago, since I have two different type of hopping parameters, it does not guarantee that I will be having only two different branches. I can have basically three different branches as well. So, it depends on which sequence I am considering.